Greetings everyone, it is I, your favorite insane hacker on Twitch, Omni, here to talk to you about a very important cornerstone of the Omnified experience. Something you need to understand what the fuck you are looking at when you watch one of my streams. Indeed. Today, we're going to be discussing the second of my 3 game-neutral Omnified systems, the Predator system. If you haven't checked out the video on the first of my 3 game-neutral Omnified systems, the Apocalypse system, I highly recommend you do so, as it will aid you in your journey to understanding what the fuck Omnified means. A link to that video can be found below in the description. What is a game-neutral system? A game-neutral system is hacking code, aka scary assembly code, that I've devised that can be hooked up to virtually any game, and it will provide its intended functionality. No changes required. It is literally a mod for a game that can be copy-pasted in between games, and it will work. I've never heard of anything like it being done before, and it's what allows me to be able to pick up a game and slap on the Omnified experience so quickly. But all that aside, Predator system. What the hell is it? The aim of the Predator system is to provide a general-purpose Omnified AI movement enhancer. How does one enhance movement in an Omnified fashion? By making it so enemies move faster to kill your ass quicker. So it is basically a general purpose speed hack. However, it is more than just a simple speed boost for enemies. Instead of simply making the distance traveled for an enemy X times the normal amount, other factors are considered in order to at least maintain and indeed vastly increase the deadly potential of said enemy. These factors are as follows. 1. The intention of the mob. 2. The direction of movement. And 3. The proximity to the player. Discerning the intention of the mob is rather difficult to do, more so when we're talking about a game-neutral system. Knowing whether or not an enemy is aware of us and attempting to home in on our position and murder us is very game-specific. And frankly, even if I passed to the Predator system a flag that would indicate whether or not we had aggro, it would take too long to locate this flag game to game. And the point of these game-neutral systems is time efficiency, my friend. So given that we cannot discern the explicit aggro of enemies, we instead make use of location-based discriminators, devised by myself, known as areas of influence. Here's a basic diagram of what they look like. This is from a design document for an early prototype of the Predator system, but it is essentially how it was implemented. Each area has different effects on the movement speed of an enemy, as well as different conditions that must be met for those effects to be realized. Simply put, however, the closer an advancing enemy is to the player, the greater a boost they receive to their movement. So that as they close in, they essentially swoop down upon the player's ass to deliver murder. We have 3 different areas of influence. The outermost area is the area of Indifference. The enemy is within the area of Indifference if the distance between them and the player is greater than or equal to 2 times the value of the exported parameter Aggro distance. An exported parameter is a variable with a default value that we can override in our game-specific hacks. The particular parameter we're talking about here, Aggro distance, defines the distance between the player and the boundaries of the innermost area of influence, known as the area of Aggro, which we'll go over in a bit. The default value for this is typically 20, but it varies based on how much real distance is covered by changes in axis magnitude. In the area of Indifference, enemies simply have a base speed boost applied to them, although that is optional based on the game. The speed boost here is mainly a cosmetic effect, although if we are playing a game such that you have incoming waves of enemies that start from very far away, the speed boost results in the swarming of the player by these waves even at this distance, thus no longer just a cosmetic effect. Typically we just leave them with the speed boost going because it's funny looking at all these things move fast in the distance. Other than that though, enemies this far away typically are outside the focus of the player, and they typically do not have the player in their focus. Simple speed boost suffices. This speed boost is defined in another exported parameter known as enemy speed X, enemy speed multiplier. This is the base speed boost applied to all enemies. By default this is set to 2 times. Therefore, games with the Predator system will have a 2 times speed boost applied to enemies that are far away from the player. There are reasons why you would want to disable the boost at this level, and I'd be happy to discuss those reasons if anyone's curious enough to bring it up in the comments. So that's the area of Indifference. It's the most boring area. Let's talk about the next area. The area of influence that follows is the area of Sketchiness. Enemies that are in this area are close enough to the character for their movement to be deemed sketchy-ass movement. An enemy falls within this area if the distance between them and the player falls between the aggro distance parameter and 2 times the aggro distance parameter. Essentially, if they are between the boundaries of the area of aggro and the area of indifference. In this area, the enemy receives a speed buff whose base value is again, the enemy speed X parameter. However, if the predator system determines that the enemy is moving towards the player, then that speed buff is doubled. If the enemy is not moving towards the player, then, as was just stated, movement is increased only by an amount as defined by enemy speed X. If it seems the enemy might be closing in, we want to ramp up that speed a bit, raising tensions a hell of a lot by enemies suddenly doubling in speed as they get closer. That is essentially all that happens in the area of sketchiness. Things are starting to get a little bit more hot. The area closest to the player is the area of aggro, and any enemy whose distance from the player is less than or equal to the aggro distance parameter falls within this area. In this area, we determine that the enemy is close enough to be an immediate concern to the player and is probably trying to whip their ass. Enemies that fall within this area only receive a speed buff if it is determined that they are moving towards the player. If enemies are not moving towards the player, they receive no speed buff at all, normal movement. However, if they are moving towards the player, they receive an even greater speed buff than the one in the area of sketchiness, essentially 4 times the amount specified in enemy speed X. Essentially, the base speed buff defined by enemy speed X is quadrupled, 4 times that amount. If the base speed multiplier is, for example, 2 times, then an enemy closing in to the player has the speed multiplied by 8 times in this area. This results in a blindingly fast swooping in onto our butts for murder deliverance. Speed buffs are not applied if the enemy is not moving towards us to allow for fine-tuning of enemy location, like if they're around a corner or just need to adjust their location a bit before they can close in. A speed buff here would likely cause them to over-accelerate, and they would probably need to correct their location again. There is yet another quasi-area, however, that exists within the area of aggro, and that's in an area defined by the exported parameter threat distance, which is the distance from the player where an enemy can be considered an immediate threat and can probably land an attack. By default, the threat distance is only a few units away from the player. If an enemy crosses this line, all speed buffs are removed. This is so the predator system does not interfere with the accuracy of enemy attacks. And in the majority of cases, it works beautifully. A dumb and simple speed hack can cause many unforeseen consequences, such as enemies shooting way past you when they launch a sort of charging attack. And that's because the predator system cuts off all speed buffs right before the point of impact. The majority of attacks are accurate and deadly. This is truly a big achievement and benefit to the use of the predator system. And what I've just described to you is how the predator system affects a game. You should now understand that the predator system boosts enemy movement speed and that it causes the enemy to slowly build up more and more speed until they are zooming in on us. And then the system essentially disables itself right at the critical distance so that an enemy attack can be performed normally and land on a player. The predator system is an intelligent, game-neutral speed hack system that aids the enemy AI in the killing of your ass. So now we get to talk about some technical concepts that enforcing these rules brings up. First of all, we have the notion of distance. How do we determine distance? How do we determine distance in assembly? Following this technical overview of these concepts, we'll actually look at the code a bit and see how the predator system works at that level. Shown to you now is the formula that we use to determine the distance, and it is implemented in assembly in our Omnified code base, and it is found in the function find coordinate distance. It is a simple geometric formula for finding the distance between 2 points on a plane, and we use it here. The most interesting part of this is probably the assembly required, which we'll go over. But through the use of this find coordinate distance function, finding distance is really easy, and its uses can extend beyond just the main purpose of the predator system. Indeed, I've used it in various spots in my code all over the place. Another technical concept that was bandied about during the discussion of the predator rules is the determination of whether or not the enemy is moving towards the player. The predator system makes this functionality available in the function called isMovingTowards. We determine that an enemy is moving towards the player if the change to the enemy's coordinates is such that the greatest change is occurring to the axes, that it separates the enemy and the player the most, such that the change is causing the enemy to become closer to the player. This is actually a function that I just fixed up not too long ago, prior to making this video. I just kind of let it sit broken for a bit, then sat down and sort of reimagined how it actually should do its job. And I'm very excited for the gameplay implications, since we have a predator system that is up to spec now. I say this because if you've watched some earlier Omnified games with the predator system, things are just gonna be a little bit more on point now, okay? The exact mechanics of this function and how we implemented it in assembly will be covered in the code review. The final technical concept that the predator system covers is something known as scaled base speed. All the times I mentioned the base speed buff of enemy speed X in the rules overview, well, we weren't actually using that value. We're using a derivative of that value known as scaled enemy speed X. which is the effective base speed applied, and it differs in that it takes into account the scale of the creature's size. This is only actually needed for games that implement true scale for the creatures. Typically when a game itself supports varying sizes for the same type of mobs. In games like this, larger creatures will typically move in accordance to their leg span. That is, a larger version of creature X will have a greater leg span, and therefore cover a greater distance in the same amount of steps. When a creature like this receives a speed buff, what you end up with is insanely fast, huge creatures that are miles faster than their smaller counterparts, and these zooming big guys are impossible to keep up with. This problem came about when I was Omnified Monster Hunter World, and the scaled speed functionality exists because of it. We need to scale the base enemy speed multiplier so that a smaller multiplier is applied to creatures that are larger, and in the same sense we need to scale it so that it is larger for creatures that are smaller. The formula we use is found in the calculate scaled speed function and looks like this, and it is implemented in assembly, of course. The formula is something I came up with, and it essentially results in what I've determined to be a manageable speed for a creature given its size. Most games don't implement true scale though. As you might know, the third Omnified system is the boundification system, which changes the shape and sizes of creatures randomly, constantly. And in most games I've put it in thus far, I've had to implement my own scaling functionality for character models, for which they completely lacked any trace of. This is an example of false scale, in the sense that when I increase the size of a creature, his leg span appears larger, but he doesn't actually move faster. Though this does give me an idea of adding a parameter indicating whether or not true scale exists in the game, as in I could probably actually create true scale if the scale by itself does not affect movement. And you know what, I'm gonna do that, but that's future project stuff. All of this is bottled up and mixed together, and we have our main predator function, execute predator. And this bad boy simply takes in a number of parameters and then returns an updated movement offset amount for a creature that adheres to the rules described before. AKA it gives the enemy a boost based on its directionality and area of influence the creature falls into. So there you have it, an intelligent speed hack. That's the predator system. Now we're gonna look at the code. And here we're gonna be looking at the code for our predator system functions. This is found in my Omnified common library of assembly for my game neutral code. We start off with declarations of those exported parameters we discussed earlier, the base enemy speed multiplier, the distance between the player and the boundary for the area of aggro, the distance between the player and the point at which all speed buffs are removed, the threat distance. Two other important parameters here, skip boost Y and skip boost Z. These will, when set to 1, disable boosting on those axes, Y or Z. These exist because you typically want to avoid boosting movement on the axis in which changes result in vertical displacement. Boosting vertical movements will typically result in the creature no longer adhering to gravity and getting into the sort of trouble analogous to falling through the ground or launching up into the air when simply trying to get on top of a hill. First function we're going to look at is the find coordinate distance function. This is essentially an implementation of the formula shown earlier in assembly. It takes the following parameters: the player's X, Y, and Z coordinates, and the enemy's X, Y, and Z coordinates. They can be found at these locations in the stack. These locations are following the code I have at the beginning of all my blocks of assembly, where I perform data preservation by storing register values onto the stack. Since I need to back up all my register data before doing anything, documenting the parameter locations is only useful if it takes into account this, as backing up data changes the location of these parameters. This backing up the data here, this is where you can find those parameters. So what does it do? First we take the enemy's X, Y, and Z values and throw them all into the XMM0 SC register. We then do the same for the player, loading those values onto the XMM1 register. We then do a packed subtraction operation, which will subtract the player's X coordinate value from the enemy's X coordinate value, the player's Y coordinate value from the enemy's Y coordinate value, and so on, storing it all in XMM0. We then do a packed multiply operation, which will essentially square the difference of those coordinates. Our XMM register then contains these values in the following order. The lowest word will be the Z difference squared. The next word is a don't care value. The third word contains the X difference squared, and the fourth word contains the Y difference squared. So we then do a shuffle quadruplet instruction here into XMM1, with XMM0 being the source register, with the B bit mask, which will result in the XMM1 register containing the same values as the XMM0 register for the most part. However, the lowest word, instead of containing the Z difference squared, will contain the Y difference squared. So then the add SS instruction here between XMM1 and XMM0 will therefore add the y difference squared value to the z difference squared. We then do another shuffle instruction here, this time with x1 just being the source and destination register, however, and with the bit mask here just being 1, which will cause the x difference squared from the original calculation occupying the lowest word. This final add ss instruction then adds the running total of the z difference squared plus the y difference squared with the x difference squared, resulting in all these differences squared values being added together. We then take the square root of all that stuff, which is in the x_0 register, and that is our distance. We then store that distance into the EAX register, which is as documented, where the return value of the function is stored. That's simply how the find coordinate distance function works. Next function is the calculate scaled speed function. This essentially implements the formula shown earlier, and is truly only useful for games with true scale, where larger size equals larger leg span and greater distance covered. It simply takes the 3-dimensional scale to the enemy, that is the amount that each dimension differs from normal, i.e. a height scale of 2 means the enemy is twice its normal height, and it finds the average of these 3 scales. It then divides them by the average scale divisor, 3 because we're dealing with 3 values we're averaging, and multiplies that by the average scale multiplier, negative 1.67 typically, and then adds the scaled shifter value to that, which is typically 4.675. We then divide all that by the speed normalization divisor, which is typically 3. We then ensure that the speed is such that it is not negative, which could occur for huge scales. And we then store that scaled speed multiplier in the EAX register, which holds the return value. And that's that. Let's move on to more interesting things. The is moving towards function, which determines if the enemy is moving towards the player. This is more advanced than the other functions. If the enemy is moving towards the player, the EAX register will be set to 1, otherwise it will be set to 0. The function takes the following parameters: the player's XYZ coordinates, the enemy's XYZ coordinates, and the change to the enemy's X, Y, and Z coordinates, the movement offset for the enemy. This function does some fancy stuff in order to achieve its purpose without a ridiculous number of instructions. To remind you, the function determines if the enemy is moving towards the player if the movement offset for the coordinate is greatest for the coordinate that separates the player from the enemy the most, such that the movement offset, when applied to the enemy coordinate, results in a smaller difference between the player and enemy for that particular coordinate. So how do we do all this? Well, we load x_0 with the player coordinates, we load x_1 with the enemies, and then we subtract the enemy's coordinates from the player's coordinates, and we then square that value, multiplying x_0 by x_0, doing a packed multiply. We do that so we don't have to deal with any sign nonsense, plus or minus. Following this, we have an x_0 register that looks like this when looking at the various words. The first word is the z difference squared, that is in the lowest word. The next word is a don't care value. Third word is a x difference squared, and the fourth word is the y difference squared. We now need to make comparisons between these differences. We need to figure out which coordinate difference is the greatest. So we do this like so. We copy x_0 into x_1. Then we do a shuffle quadruplet instruction with x_1 being the destination, x_0 being the source, and we use a bit mask of 87 hex, which shuffles the contents of x_1 to reflect the following, where the y difference squared is the lowest word, z is the third word, and x is the fourth word. We then do a packed comparison here with an operand of 6, which results in a greater than comparison occurring between each of these words. The results of this comparison are stored in x_0. So the first word of x_0 will contain the results of the check if the z difference squared is greater than the y difference squared. The third word contains the results of the check if the x difference squared is greater than the z difference squared, etc. If the comparison returns true, then the particular word for that comparison is set to OXFFF. Is that 4 Fs? Well, 4 Fs. If false, then it is set to 0. So we take that bit mask, which is written to x_0 as a result of the CMPPS instruction, and we check the results of the various comparison operations and make our decisions based on that. So we throw it onto the stack like so, and then we first check if y is greater than x. This was a comparison whose results were stored in the last word of the register over here, and that can be found on the stack at the offset of C. 0, 4, 8, and C is where we can find the various comparison results. So we load that result onto the EAX register, and we do a test instruction, which will clear the 0 flag if the value of the EAX register is non-zero. The value of EAX is non-zero if indeed y is greater than x. As I just said, if it is greater, if the comparison returned true, it would be set to OXFFFF, which is indeed not 0. So then in that case, the jump if not equals statement will fire and will cause us to branch to the is z greater than y label here. And in the event that it does branch here to is z greater than y, since we know that y is greater than x, then if z is greater than y, we know that z is the greatest difference. Otherwise, y is the greatest difference. If y is not greater than x, then we check if x is greater than z, determine if x is the greatest. If it's not, then z is the greatest. These other comparison checks just look at a different place in the stack, basically. We're looking at RSP here instead of RSP plus C. RSP is where the z is greater than y comparison occurred. Here we look at RSP plus 8 for is x greater than z. When we get down here, if, for example here, if it is determined that y is the coordinate which separates the player and enemy the most, then we want to check if the greatest change is occurring to the enemy's y coordinate. We just do that by taking the movement offsets for the enemy's XYZ, which is located here, storing that into the XMM0 register. We square those offsets so we don't have to deal with the signs. And then we just throw that onto the stack, and then load the squared y offset onto the XMM0 register. We then check if the squared y offset is greater than the squared x offset. Right here, the squared x offset will be stored at the stack plus 8. If it isn't greater than that, then we have to bail out of here because we already know that the enemy is definitely not moving towards us. We do the same comparison between the y and the z offset. If y is greater than the z offset, then the y offset is the offset that is experiencing the greatest change. The only thing we need to do that's left then is we need to determine if the change occurring to y is such that it will result in the enemy's y coordinate being closer to the player's y coordinate once it's applied. That's done in this is change moving towards, which all these other routines would end up calling as well if it's determined that, if for example, x has the greatest offset applied to it, or z has the greatest offset applied to it. Basically the same exact steps are followed for cases where x is what separates the player and the enemy the most, and for cases where z separates the player and the enemy the most, except we're checking if x is the greatest offset and z is the greatest offset respectively. When we get to the is change moving towards part of the code here, XMM0 will contain the difference between the value of the coordinate of interest of the player and the value for the enemy, and XMM1 will contain the movement offset for the coordinate of interest. We determine if the change is such that it will result in the coordinate becoming closer to the player by comparing the sign of the coordinate difference and offset. If the player coordinate minus the enemy coordinate yields a negative value, then the offset also needs to be negative. A positive offset would result in an even larger gap between the player and enemy. So we just basically check here if the sign of the difference, just down right here, is the same as the sign of the offset. And if they are both negative or both positive, we can finally determine the enemy is moving towards the player and set that EAX return register to 1. Whew. All right, after that fun little function of code here, we finally have the main predator system function. This is what we call from our game-specific code, what we hook into to add predator system support. It takes a number of parameters here: player's coordinates, the enemy's coordinates, the enemy's dimensional scales, and the enemy's current movement offset. At its conclusion, it returns an updated movement offset for an enemy's x coordinate in the EAX register. EBX will contain the updated offset for the y, and ECX will contain the updated offset for the z. I won't go over every line, but just generally, we do a lot of backing up here, and we must first take the dimensional scales and then pass them to the calculate scaled speed function, which is what we do here. We use the return result of this as the base speed buff for the enemy. We then find the distance between the player and the enemy by calling find coordinate distance and store it in XMM5. We then compare that distance to the boundaries of the various areas of influence. If the distance is less than that of the aggro distance, we know the enemy is in the area of aggro, so that's where we go. Direct execution 2. If it was between the aggro area and area of indifference, it is in the area of sketchiness, which is what we jump to here. Otherwise, we are in the area of indifference. If we're in the area of indifference, we simply load the scaled base enemy speed multiplier, which is stored in XMM4, and load it to XMM8, which is basically going to hold the final speed buff to be applied to the offsets. And then we jump to the exit routine. If we're in the area of sketchiness, we check if the enemy is moving towards a player. The calling is moving towards. If they are not moving towards the player, we exit with just the scaled speed buff being used. Otherwise, we double the scaled speed buff and exit with that. If we're in the area of aggro, we first check if the enemy is within the threat distance. And if we are within the threat distance, we don't load any speed buff at all. And we just get to that exit routine. Otherwise, we check if the enemy is moving towards the player. If the enemy is not moving towards the player, we exit out with just a default speed multiplier being applied. This is typically a default of 1.0, so no speed buff is being applied. Although, we could tweak that if we wanted to for some particular reason. But for all intents and purposes, it's not moving towards the player, no speed buff. If the enemy is moving towards the player, we double that scaled speed base multiplier here, and then we double it again. I guess we could have just done one multiply here of 4 times, but whatever, who cares? And then we hit up that exit routine. In the exit routine, we look at the skip boost y and skip boost z parameters and forgo boosting those axes as appropriate. Otherwise, we take our effective speed multiplier, found in XMM8, multiply the z offset by that, and store that offset in ECX, and shuffle XMM3 so that The Y offset is the lowest word. XBIM3 is what's holding those initial movement offsets, by the way. We multiply that then by the speed multiplier, unless we're boosting Y. And then we store that into the EVX register. We do one more shuffle here. We put X in the place of the lowest word, and we multiply that by the final speed multiplier and store that in EAX. What then follows at the end here is some limit checking. For some games, due to some complicated physics, we can start to reach speeds where it is impossible to slow down, and an enemy may phase out of existence. It is an interesting topic, and one I will not get into now. For some games, we just need to check and ensure that speeds don't exceed a certain amount. If they do, we need to limit the movement to slow the creature down. That's what the remaining code is for. Many times we don't have to rely on this limiting functionality, and we don't have to use it. A lot of times, the key for us not having to rely on this is finding the perfect initiation point for the Predator system that relies on us finding the placing code where offsets are about to be applied to an enemy coordinate way before that updated value is written to the coordinate location in memory. It's a complicated topic, and I covered in the Predator videos where I'm hooking the game up to the actual Predator system. And that's it for the code. By calling this function in the place where offsets are about to be applied to an enemy's coordinates, you essentially add support for the Predator system and make the game that much more omnified. That's the Predator system, folks. I hope you found it illuminating, and hopefully maybe you understand a bit more now what makes an omnified game omnified. Do you appreciate this content? Think it's cool and nifty? There's really no better way to support me than to hit that subscribe button. It's a huge morale boost, and it lets me know that there's interest in this difficult to produce content. If you want to take it a step further, you gotta check out that live omnified gameplay, baby. And the only place you can do that is on my official Twitch channel, found at twitch.tv/omni. Have any questions? Leave a comment, or join my Discord and ask there. No question is too stupid. I was a beginner of this stuff too, for the most part, not too long ago. Thank you for your attention and time, and have a kick-ass day. See you all next time. Bye.